Hello guys, I am Onov Mundol, lecturer of Mechanical Engineering Department of Camellia Institute and Technology and Management. Uh, I am taking the subject PCME 502. The subject name is Solid Mechanics. So to capture this subject very well, you should know the strength of material first. So if you have a very well knowledge of strength of material, you can capture this subject. So uh, uh, we start with the chapter named as analysis of stress. Okay, so what is stress? Stress is a internally resistive force per unit area. When an when an external force is applied to a body, then according to Newton's third law of motion, that every action have an opposite and equal reaction. So as per the Newton's third law of motion, the body will resist this applied force, and this resistive force is must this resistive force is actually internally resistive force. So what is stress? So stress is nothing but internally resistive force per unit area. Okay, so stress is nothing but internally resistive force per unit area. So if the applied force is F and and area is A, then stress sigma is equal to F by A. Okay, here we have to analyze a stress component in a tensor form. Okay, so at first, to do this we have to know body force, surface force, and body force, surface force, and stress vector. Okay, okay, so at first we have to draw a diagram. Consider a body occupying a region of space referred to a rectangular coordinate system xyz. Suppose this is the coordinate system x, y, z, and this is the origin point O. In general, the body will be subjected to two types of forces. One is body forces. Body is subjected to two types of forces. Number one is body forces, and the second one is surface forces. The body forces act on each volume element of the body. And examples of these kind of forces are gravitational force, the inertia force, and the magnetic force. The surface force act on the surface of the surface or area elements of the body. So the body force, I repeat, the body forces are the gravitational force, the inertia force, and magnetic force, and it act on each and every volume of the body. And the surface forces act on the surface or area only. So and body forces and then surface forces. Okay, so when the area considered lies on the actual boundary of the body, the surface force distribution is often termed as surface traction. So at first I have to draw a body. Suppose this is a body. This is the point P. Suppose these all are reaction force. These are applied force F1, F2. This is reaction force R1, R2 and R3, and this is applied force F3, and this is internally distributed resistive force. Okay, so when the area when the area considered lies on the actual boundary of the body, the surface force distribution is often termed as surface traction. So when the area considered lies on the surface or area element of the when the area lies on the actual boundary of the body, the surface force distribution is often termed as surface traction. Okay, so in this figure the surface forces are F1, F2 and F3, and the concentrated force, these all forces F1, F2 and F3 are the concentrated surface force, while P is the distributed force, and the support reactions, that is R1, R2 and R3, are also surface forces. It is assumed that under the action of both body forces and surface forces, the body is in equilibrium. So the main point is that F1, F2 and F3 are concentrated surface force, while small p, and this force small p is distributed force. Okay, the support reactions R1, R2 and R3 are also surface forces. Okay, so it is assumed that under action of both body and surface forces, the body is in equilibrium. So it is assumed that under action of both body and surface forces, the body is in equilibrium. Okay, so let P is a point inside the body with coordinate x, y, z. Uh, we have to cut the body in two parts. To analyze these body forces or surface forces or the stress vectors, we have to cut this body on this body in two parts. Okay, so I draw the two parts. This point is P. Okay, this is C and this is D. This part is denoted as D and this part is denoted as C. So this point P, this point P, it is a point inside the body with coordinates x, y, z. Oh, okay. Let the body if we consider let P is a point inside a body whose coordinate is x, y, z. Okay, so let the body cut into two parts as I have done before by a plane 1 1 passing through point P. So so this body is cut by a plane 1 1 passing through the point P. So if we consider the free body diagram of C and D, then each part is in equilibrium under the action of externally applied forces and the internally distributed forces across the interface. And in part D, in part C, let delta A be a small area surrounding the point P. So this area we can term as delta A. Okay, and in part D, the corresponding area at P dash, this point is known as this point is P dash, and this A area we can denote as delta A dash. These two areas are distinguished by their outward drawn normal N1 and N1 dash. This is N1, N1. It is normal. So what is N1? N1 is the normal outward drawn normal from area delta A, and n dash 1, this is n dash 1, n dash 1, n dash 1 is the outward drawn normal from the area delta A dash. So I write this n1 is the other. Okay, at first I have to write that delta A is the small area surrounding the point P at part C. Delta A dash, the small area surrounding the point P dash surrounding the small corresponding area Why I am writing this? Because if we add these two part, we see that this area, small area, and this small area is equal and same. I mean these two areas, if the part is a solid part, if this part is uncut, then these two small area is same and placed in equal position. So delta A dash, the small corresponding area surrounding the point P dash at part D. Then I'm writing that what is N1? N1, it is an outward normal drawn from delta A. N1 drawn from P. N1 dash, it is an outward normal drawn from P dash. Okay. The action of part C on the action of part C on delta A dash at point P dash can be represented by the force vector delta T1. So let the action of part C on the area delta A dash is delta T1. And the action of part D, so delta T1, the action of part C on delta A dash at point P dash is delta T1. And the action of part D, delta T1 dash, the action, so delta T1 dash it is the action of part D, the action of part D on delta A at point P. Okay, so here we can see that delta A, it is the small area surrounding the point P at part C. Delta A dash, the small area corresponding the small corresponding area surrounding the point P dash at part D. N1, that is an outward normal drawn from P. N1 dash, it is an outward normal drawn from P dash. So delta T1, it is the action of part C. Look very carefully. It is the action of part C on delta A dash at point P dash. It is delta T1. And what is delta T1 dash? It is the action of part D on point P at delta it is the action force of D on the area delta A at point P. This is delta T dash. Okay, so as we assume, so going to next page, I'm going to next page. As we assume that delta A tends to 0 and the ratio of delta T1 by delta A tends to definite limit tends the ratio of delta T1 by delta A tends to definite limit. So we can write lim delta A tends to 0, delta T1 by delta A is equal to dt1 by dA suman T1. Similarly, at point P dash, the action of part C on D as delta A dash tends to 0 can be represented by a vector lim delta A dash tends to 0, delta T dash 1 by delta A dash suman dt dash 1 dA suman T dash 1. Okay, so these two vectors, that is T1 and T1 dash, are called stress vectors. So vectors T1 and T1 dash are called stressed vectors, and they represents forces per unit area acting respectively at point P and P dash on planes with outward drawn normal N1 and N1 dash. So vector T1 and T1 are called stress vectors, and they are easily represented as forces per unit area. See that this is the force and this is the area. So force per unit area acting respectively at P and P dash on planes with outward drawn normal N1 and N1 dash. So see that this is the stress vector force T1, delta T1. This is the small area delta A. This is the small stress vector delta T. Not stress vector. This is small action force T1, and this is the small unit area delta A. So this ratio, that force per unit area, that is known as T1, which is stress vector. As per the formula of stress, that stress is the force per unit area. So as we can see, that's what is stress. Stress is the resistive force per unit area. So we can see that the part C resist the force T1 on part D. As this is the vector, so this forces is not normal to the area. This is the, as this is vectors, this is deflected by some angle. So particularly this is a force, but this is not straight or the normal to the area, because this is a vector and it is inclined by some angle. Okay, so as this is the internal action force T1, del T1, and this is acting from the area delta A dash. So it can be written as the delta the delta T1 by delta A as force per unit area is equal to T1. Okay, that can be known as the stress. So T1 and T1 dash is T and T1 dash T1 and T1 dash are called stress vector. So we further assume that the stress vector T1. So look that the stress vector T1 and T1 dash representing the action of C on D at P is equal to the magnitude and opposite in the direction to the stress vector T1 dash representing the action of D on C. Look, we can see that del T1 by del A is equal to the T1. So that T1 is the stress vector. T1, it is the stress vector which representing the action of C on D at P is equal to the magnitude of the stress vector T representing the action force of C on D at P is equal to that is equal in magnitude and opposite in the direction of stress vector t1 dash. So this is this stress vector t1 and this stress vector t1 dash, this stress vector t1. So this is the this is the direction of t1 and this is the direction of t1 dash. These two stress vectors are equal in magnitude but opposite in direction. So according to Newton's third law, we can write that t1 is equal to minus t1 dash. So the stress vector t1 representing the action of C on D at P dash is equal in magnitude and opposite in direction to stress vector t1 dash representing the action on D action of D on C at corresponding point P. So 1 minute. Similarly at point P dash the action of point C. Okay. So according to Newton's third law of motion, Newton's third law. So the stress vector T1 representing the action of C on D at P dash is equal in magnitude and opposite in direction to stress vector T1 dash representing the action of D on C at corresponding point P. So according to Newton's third law, we can write T1 dash is equal to minus T1 dash. Okay, so this is the overview of this analysis of stress. The first topic, that this is the definition of stress, then the body force, surface force and the stress vector. This is the explanation of this explanation of the stress vector. This is the diagram of a body in XYZ coordinate. This is in N1 T1 and del T1 dash. So this is the analyze and the explanation. This is the analysis and the explanation of the this is the analysis and the explanation of the stress vectors. So this is the formula for the stress. This is the formula for the stress vector and T1 and T1 dash, and at last we find that we can write by according to Newton's third law, T1 is equal to T1 dash. Thank you.